Hello. Hi guys, good morning. Welcome back to a new video. See, although this was an easy question, still I see it has a lot of less summations in comparison to question number 2. Question number 2, 1, 2 were easy. This was question number 3. Although it was simply a brute force question, but still it has a very less summations. I don't know why. Maybe people thought of it something very complex. It's the only reason people don't understand. You have to always look at the time complexity of the solution which you are thinking, and brute force will for sure very easily work. Let's see what the problem says. It simply says that we are having an array ARR of size n. Okay, and then we have to find the string ARR answer, basically string array answer of size n, same n size. Now what is this answer array of size n? Answer of I is the shortest substring of ARR of I. Again, that's the shortest substring of ARR of I, which does not occur as a substring in any other string in ARR. We will see with the example itself. If there are multiple such substrings, which is if there are multiple such shortest substrings, then we have to return the one which is lexicographically smallest. So for example, if for answer of I have like a couple of variations. Let's say if the valid candidates, let's say are ABC, are AB, and then say we have AA. So firstly, we will take the smallest length ones, so this will be discarded. Now in the other lengths which are remaining, I will again go and take the one which is lexicographically smallest. So this will be my answer. Cool. Now let's see, let's simply check with this example. So we have a CAB, we have a AD, we have a BAD, and we have a C. One, again, I'll simply go by the basics. What problem asks us to do? It simply goes and says that I have to go and get all the substrings. Okay, so let's take the substrings of all the indexes. Here I is equals to 0, I is equals to 1, I is equals to 2, and I equal to 3. I'll get all the substrings. The substring are CA, CAB, A, AB, and B. This is a substrings, again non-empty substrings of index 0. For this A, AD, and D. For this B, BA, BAD, A, AD, and D. For this C. Okay, I've got all the substrings. Now next thing was answer was shortest substring. Okay, I'll go and look for the shorter one, but firstly that does not occur as a substring in any other string in ARR. So this string, this substring C, it should not occur in any other, it should not occur in any other, it should not occur in as a substring in any other string. So in this strings, in any other, again I'm talking about this specific string C, it should not occur in any other strings substring. This is a list of all these other strings, and this is the corresponding substrings. So this substring of this specific string, it should not occur in any other substrings of the other strings, right? So this C, it should not occur here. Oh, it has occurred here. So this is not a good candidate. Good, not good. CA. Oh, CA is a good candidate. A CAB. Oh yeah, it's a good candidate. A is not a good candidate. AB. Okay, AB is a good one. B. Oh, B is not. So I have these three as the good candidates. I have to get the minimum length, because if you saw shortest substring, so the one having the shortest length, you will see 2 length, 3 length, 2 length. So for sure I will take 2 length. This is gone. Again for length of 2, one which is lexicographically smaller, CAAB. Okay, AB is the smaller, so answer is AB. For answer of I of 0, answer I0, my answer is AB. And similarly I'll go on and do it for all the other indexes. For example, for the next index, I'll go on. Okay, my index is 2. I need to know which is the smallest possible substring of this specific index, which is not in any other substrings. So I'll go and check for, simply go and check for A. Is A there? Oh yeah, A is there. So it's not a good candidate. AD, not there. AD. Oh, AD is a good one. Cool. Now sorry, I missed one thing. Here it is, AD. So okay, A D is not a good one. Sorry, D. Oh yeah, D is not a good one. So okay, I have no good candidate, so I have to do an empty string. And same way I'll keep on doing. Now you might ask, Aryan, that seems a very costly operation. Yeah, it is. First thing is you are generating all the substrings of a given string. So first is, how many strings are there? I'll simply go and ask him, what is my n count? N is the number of strings. Here my n is 4. So what is the n count? My n count is 100. My n count is 100. I have at max 100 string. But okay, what is the length of each string? Length of each string is at max 20. So length of each string, let's say size, it's at max 20. Right now my size is 3, but it is at max 20. So one basic question, how many substrings can be there of a size? Simple, n square. If I have a string of size n, I can have n square substrings. If I have an array of size n, I can have an n square subarrays. So if I have a string of size 20, I can have at max 20 into 20 number of substring for one string, and I have similarly 100 strings. So total I can say I will have 100 into 20 into 20 substrings in total. Okay, that's got to be my substrings. Now a very basic operation. If I want to know the answer of I, answer of 0, again I can just do this pre-computation so that I have things handy with me, which gives me, okay, what all substrings I have. Okay, I have all these for the index 0, all these for index 1, all these for index 2, all for index 3. I can keep that handy with me. That's one thing I have done a pre-computation right now. Even if you don't want it, you can just see what will happen later on. Now, next task for me is, okay, remember this is our new search space. Aryan, what do you mean by search space? Simple. If I take a specific string C, I need to go in the entire other indexes, and roughly this will give us a count of 100 into 20 to 20. This is my search space. Again, let's take it as and say 4 into 1, 2, 3, 4. 4 into 1 is 4. This is my search space for searching this string inside this entire search space. So I can simply do and go one thing. I'll simply do one thing. I am at this index. I'll go on to all the substrings and I'll go and search this substrings in this entire search space. Aryan, how you will do it? I can simply say, no, I have a string C. Let's take I have a string CA. Now, firstly, my first operation is go on to all the substrings in this specific string. So how many substrings I can have? I can have 20 into 20 substrings. I have to go on to all those substrings for one string. Now for that one string, I will have to go and ask, bro, are you in this portion? Bro, are you in this portion? So I will go and ask, bro, are you in this portion? So I will have to go and iterate on all the indexes. Let's say I have 100 again. I have 100 indexes, and for every index I can have again 20 into 20 such substrings. 20 into 20 such substrings I can have. So this is my search space, and you can see again this is my search space. So I'm searching for the current index in this search space. Okay, great. And simply you will keep on doing that, and simply you will simply keep on doing that. Simply you can keep on doing that on all the indexes. Okay, that is you did it for the index 0. You will repeat that for all the indexes. You have in total 100 indexes. Repeat that for 100 indexes. So you will simply say, okay, it is 4 into 1e4 multiplied by 4 into 1e4. That 8 into 1e8. That seems a bit edgy for Leetcode. That is under 1 second, but that's a bit edgy. Edgy as in, okay, that's just near the, just about to. Maybe it can give TLE, maybe it is not. How can we optimize? Again, we just want a very small optimization. Very small optimization. What can we do for that optimization? For sure, we'll have to go on to all the indexes. For every index, I will have to go and check for all the corresponding substring for that index and see which is a valid substring. What I mean by valid substring is that that specific substring should not occur anywhere in the other substrings. So again, for this specific, again, I have 100 indexes. I will have to go on to all the indexes for all the substring of that index to go and look for if that specific substring, let's say CA in this case, is actually present in my other substrings or not. So I will optimize the remaining portion. How I can do that? Okay, so far I know it is 4 into 1e4. Now, I know that I will have to go and make all the substrings again and then do it for all of them. That's not required. I can do a simple pre-computation. I have gotten all the substrings already made. That's it. Now I'll simply go, I know I have to go on to all the other indexes. So I know I will have to go on to all the 100 indexes, remaining indexes, which can be 99 also. But yeah, let's take it as 100, whole number. I can go to all the 100 indexes. So far it has become a 4 into 1e6. Now for that index, if I am at this specific index, I should be able to very fastly search if I have this string CA inside this entire substrings, right? In this entire substrings, I know I can have at max. How many number of substrings? Length. Again, I'm saying simply, how many number of substrings I can have? I can have 400 substrings, and each substring is of length. 20. You saw each substring can be of at max length 20. So I'm saying I don't need to go on to all the 400 substrings. I can simply go and simply say, okay, is that substring CA, or I can right now say, is that string CA is inside these 400 substrings or not? So rather than linearly searching, I can push all these 400 strings in an unordered set. I can push all these 400 strings in an unordered set. And because of that fact, what I would do is I can simply go and search, okay, find this string CA inside this unordered set. Again, this unordered set only contains the strings of index 1, which means all the substrings of index 1. And I can simply go and find all of them. And that will be a O of 1. If I ask you to search for an integer, let's say if the integer would have been 2, and here the integer would have been 0, 1, 3, 5, and so on and so forth. If I would have asked you to search for an integer 2 in the entire unordered set of these integers, then that will be an O of 1 operation. But here in this case, it is not an integer, it's a string. You have to search a string in the entire list of string, which you have already done a pre-computation, right? That searching of a string in this, again, the string length can maximum 20. So this search, although it would have been a O of 1, but right now it is a O of 20 operation. So this will be a O of 20 operation, which I have to perform at every step. So now it will be multiplied by 20. So that will be 8 into 1e7. And that will work for us for sure. So you saw how we actually optimized it. Cool. Now we can simply see the pre-computation part for us will be 100. Again, although it is a very extreme case, it will be less than that, but it will be 100 to go on to all the indexes. For every index, I can have at max 400 substrings, and each substring can be at max of length 20, right? So this will be a rough complexity, right? Again, that's the upper bound of R. It will be 8 into 1e5. That will be the pre-computation which we have to do. Now when this pre-computation is done, I can simply now go on to all the indexes one by one to find the answer for this index. To find the answer for a specific index I will have to go on to all the substrings of that index, which I have already pre-computed and stored in my sum variable or an unordered map or something. And then I'll go on to all the indexes of this specific, I'll go on to all the substrings of that specific index. this substring, I have to go and search for all the other substrings. So the first operation was going on to all the indexes, 100. For the specific index, going on to all the substring of that index to find the answer of I, that's 400. Now for all the substrings, I have to go and check that specific substring in the other indexes, which are again 100 indexes. Now to have a check, I'll use an unordered set or a hash set to go and have a quick check, O of 1 check. Although it's a string check, so it's a O of 20 check. So that is a O of 20 check. And that's going to be solving your answer in 8 into 1 is 7 time. So final complexity is 8 into 1 is 7 plus 5 into, sorry, what is this? 8 into 1 is 5. 8 into 1 is 5. And that's going to be your answer. So this question was more of just implementation, but verifying that how you can do a small optimization, small pre-computation that you can actually get in the bounds and solve it in the range. Like it's just a simple brute force, just a small optimization of doing a pre-computation. That's it. Cool. Let's see the answer. So by default, I took an answer of I that will keep track of for all the indexes. What's the answer? By default, it's an empty string I have put. Now I'll go and have an unordered map. You remember the pre-computation I mentioned in the beginning? So my unordered map will just keep track of at a specific index, which means map of I will keep track of all the substrings in that specific, again, all the substrings, I'll store that as an unordered set. So map of I will give me at that specific index what are all these substrings in that specific index. Cool. So I'll do the exact same stuff for that specific index. What are the unordered set of all the substring in that index? Now I'll do a simple pre-computation. This pre-computation will simply say that, bro, go on to all the indexes one by one, then get the current size of the string, because you have to generate all the substrings of that, generate all the substrings of that specific string. Now when this portion is done, you will have the substring, because it is from I to J. The substring is from I to J. Get that specific substring and then insert that in your map of K. Again, K is the index. And I'm simply inserting because I know that is an unordered set. This entire portion is an unordered set. It is an unordered set. Cool. Now when this pre-computation is done, your map is ready, in which map of I will give me an unordered set of all the substrings, and it can have 400 substrings, each of length at max 20 in worst case. So this operation, you will see this will take O of n time, this will take O of n square time. Okay, let's take it as this. We have 100, this we have 100 substrings. Now each substring, the size can be of length 20, so this is O of 20, which means this is O of one operation, but the length is, this size is 20 at max. So this is a O of 20 into 20 operation, right? This getting a substring of length 20 is itself a 20 operation. So now this will simply say this operation is O of 100 into 20 into 20 into 20, which is nothing but 8 into 1e, 1, 2, 3, 4, 5. Cool. Now when this portion is done, I am good to find my answer of I. I'll simply go on to all the indexes again, one by one, which means if I just take this specific example and copy this example, it is very messy right now, but still we can simply copy this down. Now we are simply saying that this is, we are right now at this specific K. Again, this is a K itself for me. So I'm at the specific K. I will find, okay, I want to have, remember, I want to have a substring having the smallest length. So current length, I will keep track. Minimum length I want to get. Okay, we can just simply skip this current length also. That's not required for us. Yeah, we can skip that. We can simply get the length, current length from the minimum string itself. So minimum string is the string having the minimum length. If the length is still same, I want the lexicographically smallest string. So I'll by default keep track of the minimum length so far. And then if I can improvise my length, which means if I can improve, I can reduce my length, I'll compare the strings, and the one which is lexicographically smaller, that will be my answer. So I'll simply keep on going. Now how I will keep on going, I was at this specific index, so I'll have to iterate on all the substrings of that specific index. So I'll go on and say, okay, for that index k, give me all the substrings. This temp is all the substrings in that specific index k. Okay, I have got this temp, which is the substring in that specific index k. But my main task was, this is a temp, this is my temp. Check for this temp, it should not be in any of the other indexes. So I'll go on and query for the other indexes. I know I have 100 indexes. If the index is same, simply continue, because my j and k should not be same. So now I'm saying my j is this, j is this, j is this. I'm going on to all the other indexes and comparing if this string is lying in any of the other substrings or not. Cool. Now I'll simply go and check, okay, if my other substring, if my other map of j, which means the entire unordered set of substrings, if it contains my current substring temp, bro, this is not a good candidate. So I'll simply put my flag as false for this specific temp. For this specific substring as temp, I'll put, okay, this is not a good candidate. So by this, you will see I put the flag as false. And I can simply break out also, because I just wanted to know if it is present in any of the substrings later on. And I can see it is present, so I can simply break down. If it is not present, so my flag will be true for that specific temp. Now, if my flag is true for the specific temp, which means it's a valid candidate to be a good substring. If something is valid, I have to do two conditions. First, minimize the length of the good substring. And if the length is same, minimize and have the lexicographically smaller substring. So here I will have a check. Okay, if the flag is true, which means it's a good candidate. So have a quick check. If the length is small, if the current temp length is small, which means if the current good substring length is small, bro, that's a good candidate for us. So that's a good candidate. So okay, improvise the answer. So minimum string will become the temp, right? And minimum length will also decrease. It will be temp dot length. If the length is same, if my length is same, then I'll check. My temp string should be lexicographically smaller to be my answer. So I'll check, okay, my temp string, if it is lexicographically smaller, again, I can simply compare two strings. Whosoever is less will be lexicographically smaller string. So if my temp string is less than my already minimum string so far, that is my good candidate. Temp is my good candidate to be a minimum string, because it's a lexicographically smaller string of the same length. Again, length is the first preference. Small length is the first preference. Then smaller, lexicographically smaller is a second preference. So when this portion is done, you can simply say that you will have your minimum string updated out of all the substrings. So you will see that this entire bracket, it goes on all the temps. Which means all the substrings for the map of k. So at k, I went on to all the substrings, which is the map of k. I went to all the unordered set, which means all the substrings, and then I will have the minimum string for that specific map of k. And for sure, that minimum string is my answer of k. So answer of, because you remember that I'm going on to all the substrings, all the indexes one by one. So answer of k is my minimum string. And that's how I can get my all the answers done. So you will see that this is my next portion of code. Cool. And that's how I can simply return an answer. Now you simply saw what is the time complexity of this. Again, I showed you very clearly. Here I showed you what's the time. In this, if you want to see, you will go on to all the 100 indexes, right? For every index, you know that this map contained 400 substrings. So this for loop will go to O of 20 into 20 times, right? As it go to 20 into 20 times, this again is O of n. So it will again go to all the 100 times. This contains operation is a O of 20 operation, right? Then this comparison operation is again a O of 20 operation. But you will see both are different. This for loop is 120 and this is 20 itself, which is different. So I can simply say my time is O of 100 into 400 into 100 into 400 into bracket में 100 into 20, which is this, plus 20. And that's going to be you can simply ignore this in front of this. So your answer will be 100 into 400 into 100 into 20, which is 8 into 1, 2, 3, 4, 5, 6, 7. 1 is 7. So it will be 8 into 1 is 7 plus 8 into 1 is 5. And that's going to be your answer. Cool. Thanks for watching. Bye-bye. Take care. Bye-bye. Again, that's a time complexity problem, not an actual problem. Bye-bye.